So now I mentioned that I will go back to this idea. It says that we have defined a definite integral for an integrable function, but not all functions are integrable. It is kind of, it's not the same idea, but it's similar to the situation where there are some functions to which we cannot take the derivative of at certain values of x. So this is the same idea for this. For example, if I have to take the integral between 0 and any number that you want, 1, 2, or 3, or any constant, let's say just 1, of 1 over x dx, you know that this function behaves in the following manner. And, oops, it doesn't cross the x-axis. But between 0 and 1, you know that the y-axis works as a vertical asymptote. So this function, even if I'm trying to make infinitely number of rectangles to approximate its area, I will never be able to, the height of each rectangle, as the rectangles approach 0, the height of it is approaching infinity. So this is something that is not, you can't integrate that. You cannot find the integral of 1 over x between 0 and 1. You can find it between 1 and 2. You can find it for some other different values, but you cannot find the one that starts at 0 because remember that this is not part of the domain, so it is impossible to find the area under the curve if it's defined like that. So let's read theorem 3 and let's see what it means. It says if f is continuous on a closed interval, or if f has only a finite number, meaning not infinite number of jumps, like if it has 3 jumps or even 4 jumps or even 100 jumps, it's still a finite number of jump discontinuities, then f is integrable in that closed interval. So which means that when I find in this integral, that is a number and that number exists. So it says if f is integrable in a closed interval, then the limit, remember that limit that we have as n approaches infinity of the sum of all of the little rectangles that we have for I equals 1 to n. This limit actually exists, and it doesn't matter in the way that we choose that sample point inside each interval. So rather than just leaving this x of I star as any sample point, like remember if I have a function and I'm looking at this rectangle, I can pick any x that I want in the base of the rectangle for me to define the height of the rectangle. Let's just agree that we are going to use the right endpoint. So the formula, instead of looking a little funny with that x star, is just going to look like this. And then the delta x is equal to the subtraction of the limits of integration divided by the number of rectangles that you're using. And every x of I is defined as the first number in the limit of integration plus whatever number of delta x's that you're adding. For example, if I start at a, x sub 1 will be a plus 1 times delta x, which would be a plus delta x. And so this is x sub 1. X sub 2 will be a plus 2 delta x's. So this is a, this is 1 delta x. If I'm adding another one, I will be at x sub 2. X sub 3 is a plus 3 delta x. And if I'm adding another delta x, I will be finding my x sub 3. And this is something that you already practiced in the first exercise of section 5.1. You were dividing into 8 rectangles, and you found that the delta x was 0.25, so you were adding 0.25 to each of the x's that you were using. So it's kind of the same idea. So example 1 says express this limit as an integral on the interval 0 pi. So the interval gives you the first x that you're going to use and the last x that you're going to use. So this is a and this is b. And on the integral, you know that a and b are located on the bottom and top of that long s that is the integrand symbol. So the other things that you have to compare, this is using the definition of the limit in theorem 4, or the definition in this is the definition 2 that we were talking about earlier. Besides the limit of integration, you need to know what the integrand is, which is the function. So the function can be found inside of the sigma symbol. So in here, if you have the limit of the summation of this function times delta x, then this is the function that we are going to enter as integrand. So what is the function in general? The function in general raises to the third power and then adds the multiplication of that times the sign of that particular value, so for any input. So the function that we're going to put inside the integral, it actually does the same thing. It raises x to the third power and then it is adding that particular x times its sign. So this limit, as n approaches infinity, remember we're creating a lot of rectangles of the base. This would be the base times the height. It will be the same as the integral between 0 to pi of this function, which came from here, dx. So I'm just rewriting this limit that looks a little bit scary. I'm writing in a friendly manner as an integral. So something that you should notice, the sigma was replaced with the integral. If this is the summation of, you know, several items to n items, right? N items, I'm adding 8 items. And this will be kind of like a summation, but of not n items, but infinitely many. That's why it's kind of like, it's not only the summation, but it's the limit as n is approaching infinity of the summation of many, many things that becomes the integral. So this becomes this. The x that we have on the summation that could have been any x in the interval now becomes simply x. And the delta x, how wide the rectangle was, becomes simply dx. So I want you to have something very clear. If we're using an integral, we're going to learn 2 different ways of dealing with this. This is the limit as n approaches infinity of the summation equals 1 to n of f of x sub I delta x. So sometimes we will be able to find the integral of this function between a and b by finding the limit of this expression. Now this expression, remember, it was the short way of finding f of x sub 1 delta x plus f of x sub 2 plus times delta x plus and so forth all the way to f of x sub n times delta x. But since we are writing this expression and n is approaching infinity, we're not going to be able to evaluate a limit like this. Like, what would be the limit as n approaches infinity of 1 plus 2 plus 3 plus so on plus n? Like, we haven't really learned a way. Definitely we haven't learned how to find limits of expressions that you know, are written in this manner. We can find limits of functions completely defined, but this is, we can even finish writing it in its entirety. So it is very useful to know the summation of several items to be certain formulas. So this one says if I'm adding every single number, this is the addition or the sum of the first n numbers. Okay, like if I want to add 1 plus 2 plus 3 plus 4 plus 5, if I start at 1 and add an n, and it could be 10 or 20 or 30, but n in general. So if I'm adding 1 plus 2 plus 3 plus so on, 1 plus 2 plus 3 plus n, then the answer is n times the next number or the next integer over 2. So if I'm trying to find the limit of something like this, then I can just say, oh, this is the limit as n approaches infinity of n times n plus 1 over 2. And for this, I know how to take the limit of that. But I wouldn't be able to find the limit of something like this. So these are formulas that you have to know. Now this is the sum of the first n numbers squared. Okay, so it's the sum of the first n numbers squared. So if I'm adding 1 plus 4 plus 9 plus blah 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 plus n squared, the answer is simply n times the next number times, this is not the next number, but this is double the number plus 1 divided by 6. And the other one that you have to know, this is the sum of the first cubes. So you have 1 cube plus 2 cube, which is 8, plus 3 cube, which is 27, plus blah 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 blah, all the way to n cube. So the answer of this sum is actually a very simple formula, n times n plus 1 over 2 squared. Everything is a square, even the bottom here is a square. So if you know this one, you know this one by squaring that. Now these rules are other simple ones that are going to be useful whenever we have to figure out what the summation of some terms is. This means I'm adding c n times. So when you add c n times, you're multiplying n by c. For example, what would be the summation from I equals 1 to 6 of the number, I don't know, 5? This means 5 plus 5 plus 5 plus 5 plus 5 plus 5, right? 1, 2, 3, 4, 5, 6. 6 times 5. So that's all it's saying. When you have the summation of a constant, it's just the constant times the number n. Now this one says I have a constant that is multiplying every single item. So the constant can come outside. So let's say that I have the sum from I equals 1 to, I don't know, 10 of 3i. So the 3 is a constant, so it can come outside. So this is just 3 times the summation between I equals 1 to 10 of I. And I know that that by formula is, if I'm going up to 10, it would be 10 times the next number, which is 11 over 2. And that is, well, God knows what it is, but it's not important. But this is the point, is that we can take out any constant that is multiplying the number outside of the summation sign. Now, if I have the summation of two terms, that is just the sum of these two summations. So the summation actually distributes over addition and also over subtraction, but not over multiplication. For example, if I have the summation of I squared, this is not the summation of I times the summation of I. And you can see that here in the formula. If you multiply this by itself, you're not getting the summation of I squared, you're getting the summation actually of I cubed. So the summation does not distribute over multiplication. The summation of I squared is not summation of I times summation of I. Like, it does not distribute over multiplication, only over addition and subtraction. Now example 2 says evaluating an integral as a limit of Riemann sums. So I'm going to be able to evaluate something like this using a Riemann sum, but let's first figure out what part A means. It says evaluate the Riemann sum for this function taking the sample points to be the right endpoints, and A is 0 and B is 3 for 6 rectangles. That's what this means, 6 rectangles. So I'm going to use a Riemann sum for that. And so you begin by first drawing your x-axis between 0 and 3. So we're going to have 6 intervals. 3 minus 0 is 3, divided by 6 is 1/2. So we're going to have 1/2, 1, 1.5, 2, 2.5, 3. And then this is going to be our x sub 1, x sub 2, x sub 3, x sub 4, x sub 5, and x sub 6. Since we're using the right endpoint, then we're not counting this one. This is the one that is going to determine the height of our rectangle. So the first thing we have to do is find actually how much is f of 0.5, f of 1, f of 1.5, and so on, so that we know how tall the heights are. Now in this case, I'm saying height, meaning how tall the line is going to be. But if you have an f of 0.5 being a negative 2.875, then you know that you're going to go actually down rather than up. So you're going to go down this way. Then this one is -5, this one is -5 and some change, this one is -4, this one is 0.6, so it's going to be very little, and then this one is going to be 9. So that's how you're going to construct those rectangles. Some rectangles are actually below the x-axis, and those are the ones that are going to be counted as negative, and these ones are the ones that are going to be counted as positive. Since the base of each rectangle is the same and equal to 1.5, then the Riemann sum is going to be simply 1/2 times the sum of all the heights, because the base is the same for every rectangle, so I'm just factoring it out. And you're adding all the heights of the rectangles, the positives and the negative ones. So the result is a -3.93, which means, going to our graph, this function is negative and positive. So the Riemann sum in here, definitely there's more areas below the x-axis than above. That's why our number is a negative number rather than a positive one. So the integral between 0 and 3 is going to be a negative, meaning the negative area won over the positive area. That is when we're using actually 6 rectangles. But if we want to evaluate the limit for the sum of n rectangles, then the calculations are going to look different. The calculations are going to depend on n, because is n the number that we are trying to make very, very large by applying the limit as n approaches infinity. So the integral, by definition, is the limit of this summation. So the limit of this summation is, since we know what f is actually every item cubed minus 6 times that item. Now, the only thing that are shown here are the simplifications using the properties for summation. So for example, in here, I know that if I'm cubing this term, this will be 27i cubed over n cubed. And then in here, I'm just multiplying 6 by 3, which is 18. Now, since I have the summation of a subtraction, I can just simply say that is the summation of the first term minus the summation of the second term. Now, after this, then I know that 27 times 3 is 81, 18 times 3 is 54, and these ends can come outside the summation because they are considered constants. The only one that is not a constant inside the summation, according to this, is the I. So in here, the I has to stay inside. Now, the summation of all the first cube numbers, we know that by formula is n times n minus 1 over 2 square, and we got that from previous slides. And then the summation of the first n numbers, or the first I numbers, is n times n plus 1 over 2. So in here we can simplify the n's, and then we are having this expression for which we can apply the limit as n approaches infinity. As n grows very large, this is almost 0, and this is almost 0. So it turns out to be simply 81 over 4 minus 27, which is negative 6.75. Compare this number with the number that we got before using the Riemann sum. So using the Riemann sum, only 6 rectangles give us this value, which is a little bit off from the actual one using, using n rectangles and n approaching infinity. So the more rectangles, the more accurate. So the actual value of the integral is this one. An approximation, a very rough one, would be using a Riemann sum with only 6 rectangles. If you want a more accurate, you will pick more rectangles, and if you want the exact one, the actual one is actually this one. Now, using limits is only one way of finding the value of an integral. We're going to learn other ways to find that, so please do not be scared about how overwhelming finding the limit of this was. We're going to learn easier ways to do that. So looking at a picture that is a lot cleaner, as n is approaching infinity, we're going to have these rectangles to fit right exactly with the area that we're trying to find. Since the integral for this function is worth negative 6.75, that means that whatever area is here minus the area that is in here, that subtraction is worth negative 6.75. In here, just to go over the same idea, if instead of 6 rectangles you had 40 rectangles, this would be the picture, and definitely this value would be the Riemann sum for 40 rectangles. It would be a lot closer to the negative 6.75, which was the actual one. So this is closer compared to the one that we got for 6 rectangles. For 6 rectangles, we were far off. For 40 rectangles, we're getting closer. For 100 rectangles, it will be even closer to this number. As you can see from this table, if I'm using 100 rectangles, or 500, or 1,000, or 5,000, this number is approaching negative 6.75. Now it says, we often choose the sample point to be the right endpoint, but sometimes it is better to use the midpoint in every rectangle. So the picture is gonna look, if I'm finding the area between 1 and 2 and I want 5 rectangles, so it will be between 1 and 1.2, between 1.2 and 1.4, between 1.4 and 1.6, between 1.6 and 1.8, and between 1.8 and 2. So the midpoint between 1 and 1.2 is 1.1. That's going to be the height of the rectangle that I'm going to use for my Riemann sum. Between 1.2 and 1.4 is 1.3, and the height of my rectangle is going to be f of 1.3. In here, the same thing, the number in the middle, the midpoint, is 1.5, so the height will be f of 1.5. This one, it will be f of 1.7, and in here, it will be f of 1.9. So that's what it means to choose the midpoint as that value. That's the sample point. So let's go back to this slide and read. It says any Riemann sum is an approximation of the integral, but if we use midpoints, then we get the following approximation. It just says the value of the integral is approximately the summation of all the areas of the rectangles using for height the midpoint in each interval. That's all it's saying. So example 5 illustrates that case. We're going to use 5 rectangles to find the area between 1 and 2 of 1 over x. We saw that the integral between 0 and 1 of 1 over x dx, this cannot be found, But if you are using other limits of integration, then yes, you can find the area. So that's why the integral is approximately whatever the length of the bases of each rectangle times every height, and every height is given by those values that I just explained before. So when we do that, every rectangle has a base of 1/5, and every height is, if the function is 1/x, that means that the height f of 1.3 is the reciprocal of 1.3, is the reciprocal of 1.5, reciprocal of 1.7, reciprocal of 1.9. At that number is this much. This is the approximate value of the integral between 1 and 2 of 1/x dx. Now let's talk about some properties of integrals which are going to be useful for us to deal with. Usually you're going to see that the limits of integration go from low to high. Like I'm writing the integral between 1 and 2 of 1/x dx. The low number is in the bottom and the high number is on top, and that's usually the case. But in some cases you are going to want to switch it orders. So the integral between 1 and 2 is going to be the same as the integral between 2 and 1 of the function. However, when you switch orders in the limits of integration, you just have to put a negative in front, and that's all you have to do. Okay, so sometimes this is going to be convenient, and whenever you're changing the limits of integration, the order, you just have to put a negative in front, and that's all it means. Now the other thing that you have, if you have any function and you're integrating from a number a to a number a to itself, then definitely there is no area there, so the area is 0. So this is something that is very, the idea is simple and sometimes it's useful. So the integral between a and a is 0. Now let's read some properties that are going to be very similar to the ones for derivatives. If I'm integrating a constant between two numbers, then it's just the difference of the numbers times that constant. For example, if I have a graph, I don't know, y equals 2. Okay, so if I'm integrating between 3 and 7, so what would be this area? If the integral between 3 and 7 of the function 2 dx will be 2 times 7 minus 3, which is 8. And that's true because if this is worth 2, between 3 and 7, this is worth 4, and the area is definitely 8. So this is true whenever c is a constant. The integral of the sum of two functions is the sum of both integrals, and that's something that is fairly simple. So the integration distributes among addition and subtraction. That's what I meant, yes. Now if you have the integral of a constant times a function, the constant can come outside the integral. Okay, and that's something that is going to be useful. So this is property 1, and for any c, the height of this rectangle is c, the base is length b minus a, therefore the area is going to be the multiplication of both. So that one is checked. Now the next property, this is not as simple to see, but it's true. If I'm adding the area under f plus the area under g, I'm going to have a function that looks like f plus g. So the area under f plus g is simply the area under f plus the area under g. In here they do overlap, but if I cut out this piece and I put it on top, that's what I get. Now it says example 6, use the properties of integrals to evaluate this. So since I'm having the integral of a sum, I know that I can split it into two integrals, the sum of these two integrals. Now this is the integral of a constant, so I know that this will become 4 times 1 minus 0. Now in here I have 3x squared. The 3, which is a constant, can come outside the integral sign, and that's why it's in front now. Now the integral of x squared, remember the function x squared, between 0 and 1, we saw it from the previous section that this was 1/3. So this will be plus 3 times 1/3. So this is 4 times 1 plus 1, and this integral is 5. See? You see? This answer, we got it from section 5.1. We're going to learn how to use these in the future, so but don't be upset about this. Next section, this is coming up, but for right now, you know that this is true and just go with it. And I'm just, here I'm simply applying the properties of integrals. Now, the other property that is very interesting is saying, if I'm integrating the same function between two numbers, I don't know, let's say between 0 and 5, and I'm adding the integral between 5 and 7, then this can just be written as one integral. Where did I start? Well, whatever number. I think I started at 1. Let me just put numbers. So if I'm integrating between 1 and 5, the same function, okay? And I'm adding the integral between 5 and 7 of the same function, that's the same as integrating from 1 to 7. So 1 to 5, 5 to 7, that's the same as 1 to 7. That's not the way we write it, but you get the idea. And this is the beautiful picture of it. I have one function f for both of them. If I'm integrating between a and c and b, that's just the same as integrating from a to b altogether. Almost there, I promise. So now in here it says if the function is positive and we have a less than b, then this integral is going to be a positive number, or 0. Now this one says if f is a function that is above g, or sometimes equal to, but mostly above, for any numbers between a and b, then definitely the integral as a number, this number will be bigger than this one. And then it says if there is a function f for which I can find two numbers, one that is the lowest and one that is the highest for f, then definitely the integral between these two values of x is going to be bigger than the area generated by the difference of these numbers multiplied by that low number, and definitely it's going to be less than this is the area of the rectangle formed by big M, and this is the area of the rectangle formed by small m. This is still a from a to b, so this will be length b minus a. I choked a little bit there for a little bit, but let me explain it now in here. I have my function f for which there are values, let me call this small m, let me call this capital M. So this is the highest value that f can take, and this is the lowest value that m can take. So the value of the integral between a and b, this area, is going to be a number that is going to be between the area here, right? You can see how the integral of f would be larger than this small area here, but still is smaller than the area that I can get by multiplying b minus a times large, which is right here. So that number is going to be in between this number originated by this area and the small area right there. Beautiful. Now go to sleep. I mean, do your work. Bye.